Okay, so this is the second part from practice problems, chapter 13. So let's continue working. So I'm going to move now to problem 11, and in problem 11, if a gas at 1 atmosphere, pressure 1 atmosphere, and volume 2 liters is compressed to 1 liter at a constant temperature, what is the new pressure? So directly, guys, use this equation right here. So we have P1 V1 is equal to P2 P2 V2. So P1 V1 is equal to P2 V2. Now the new pressure, which is P2, is equal to P1 V1 divided by V2. So we have 1 atmosphere times 2 liters divided by 1 liter, and you will see that the new pressure is equal to 2 atmosphere. Okay, and the right answer is C. Okay, I will move now to the next problem. So for a gas at 2 liter and 27 Celsius that is heated to 127 Celsius, okay, at a constant pressure, what is the new volume? So now I have V1 over T1 is equal to V2 over T2. This is the equation that you need to use, guys. So we have now V1, I have 2 liter over 27 Celsius, that's equal to the new volume V2 divided by the new temperature, which is 127 Celsius. So you will end up with V2 is equal to 2 liters times 127 Celsius divided by 27 Celsius, and that's equal to. We need now to use the calculator. So we have, let's refresh the calculator. So we have 2 times 127, that's equal to, and then we divide by 27, so that gives us like 9.4. 9.4. Am I right? Do we need to convert to Kelvin? I believe so. I believe so. I believe we need to convert to Kelvin. So I have 127 Celsius and 27 Celsius. So let's do with Kelvin and see what will happen. Okay. So let's do that. So again, the equation, I will write the equation here. I will keep it here. So V1 over T1 is equal to V2 over T2. So relation between volume and temperature. So the 27 plus 273.15, so that's equal to, I have 7, 8, 9, and I have 7 and 3, so that's going to give me here 400.15 Kelvin. Okay, and for 127 Celsius, 127 plus 273.15, that's going to give me here I have, it needs to be 300. That's a typo, so I have 300 here. So 200, so 73 plus 27, that's going to give me 100. So that means I have 300. Now I have 127 plus 273.15, so this is going to give me 400.15 Kelvin. If I apply my equation, so I have V1 2 liter divided by the original temperature, which is 300.15, that's equal to the new volume divided by 400.15, so Kelvin, so V2 is equal to 2 times 400.15 divided by 300.15 and liter. So that's equal to, I have 800.15 divided by 300.15 liter. So let's divide them and see what we will get. Okay. It is actually like 8 divided by 3. 8 divided by 3. So 8 divided by 3, that's equal to, say, I have 2.6. So you can see A is the right answer. So I have 2.6. So 2.54, 2.6, they are pretty close. So we can pick 2.54. So this is the right answer. So that means, guys, you need to convert from Celsius to Kelvin when you do this kind of problems. Okay, that's pretty good. Now I will move to number 13. And for number 13, I have a relation between pressure and temperature. So I have a gas at pressure 100 kilopascal and temperature 300 Kelvin is heated to 450 Kelvin at a constant volume. So the volume is constant. So what I can do this equation. So I have P1 over T1 is equal to P2 over T2. Initial pressure, final pressure, initial temperature, and final temperature. And from here we can solve for the new temperature. So P2 is equal to P1 times T2 divided by T1. Okay, so now I can do P2 is equal to P1, so P1 is 100 kilopascal times T2, which is 450 Kelvin, and I divide the whole thing by 300 Kelvin. So that's going to give me 550. So let's do that. So we have 100, 400. So we can do like 550 kilopascal divided by 300. So let's see. That means we have 5.5 divided by 3. So 5.5 divided by 3, that's equal to, I have 5.5 divided by 3, so that's equal to, so I have around like 1.8. Yeah, and 1.8 is pretty close to 2. So the answer should be oh, this is in atmosphere. So once we get kilopascal, yes, so once we get the answer in kilopascal, we need to convert it to atmosphere. Okay, so I have 1.8 kilopascal. That's great. So now we need to convert from Pascal to atmosphere. Okay, so 1 atmosphere is equal to 1 point, let's try to figure out this conversion. need to convert from Pascal to, I don't have it in my mind right now, so I think the good idea, so we need to convert from Pascal to atmosphere. I believe it's 1.01, something like that, times 10 to the power 5, something like that. So 1 Pascal is equal to, approximately is equal to this. So let's have here, okay. So this is the right, this is the right conversion that we are looking for. So 1 atmosphere is equal to 1.01 times 10 to the power 1, 2, 3, 4, 5. So 1.01 times 10 to the power 5 Pascal. Okay, so this is the conversion that we are looking for. So let's now add it here. So one atmosphere is equal to 1.01 times 10 to the power 5 Pascal. Okay, so 1.8 times 10 to the power 3 Pascal will give me X, something that I don't know, and 101 times 10 to the power 3 Pascal gives me 1 atmosphere. So if I solve for X, you will see that X is equal to 1 atmosphere times 1.8 times 10 to the power 3 Pascal divided by 101 times 10 to the power 3 Pascal. So let's see if I'm right. I have 1.8 kilopascal. Did I do everything right here? So I have here 100 kilopascal and 300 Kelvin, 450 kilopascal. So here is the problem, guys. The problem is here. So that was my mistake. So yes. So I think I should have multiplied. So I have here like 450 times 100, and that was my mistake. So now let's do these corrections. let's do these corrections. So I have P1 over T1 is equal to P2 over T2, and we are looking for the final pressure. So we have P2 is equal to P1 T2 divided by T1. So my mistake, I just added those two numbers. That was a typo, and I should have multiplied them. So I will multiply them right now. So I have now P2 is equal to P1, which is 100 kilopascal, multiplied by 450 Kelvin, and then I divide the whole equation by T1, which is 300 Kelvin. Okay, and I still have this conversion. I have that 1 atmosphere is equal to 101 times 10 to the power 3 Pascal. So I already have this conversion. So we Googled this conversion. Okay, so now we will have, so we have 100 and 450, so that's going to give me 450. Okay, that's right. So we have 450 divided by 300, and we have 100 from here, and we have kilo from here, so that means we have 10 to the power 5 Pascal. That's great. So if I divide 4.5 divided by 3, so let's do that, and now I believe we will have the right answer. So I have 4.5 divided by 3, that's equal to, I have 1.5, so we'll end up with 1.5 times 10 to the power 5 Pascal. We need it in atmosphere unit, so we need to come to this conversion. So we have 1 atmosphere is equal to 1.01 times 10 to the power 5 Pascal. Okay, so 1.5 times 10 to the power 5 Pascal actually is equal to x. Now we solve for x, and you will see that x is equal to 1.5 times 10 to the power 5 Pascal times 1 atmosphere divided by 1.01 times 10 to the power 5 Pascal. So now you will end up with 1.5 divided by 1.01, so that's equal to, so I have 1.48, which is pretty close to 2 atmosphere, one of these answers. So that give me, so that give me here 1.48 atmosphere, which is close to 1.5 atmosphere. Okay, so you can see now the closest, the closest number is 2. So it is 1.5. So that's going to give you 2 atmosphere, guys. Okay, approximately 2 atmosphere. Okay, so we just did like a simple typo. So instead of multiplying, I just added those numbers. So that was a typo, but right now we have the right answer. Okay, so that's great. Let's now move to number 15. And in number 15, let's see the relation. We have a relation between volume and temperature. So initial volume, final volume, initial temperature, and final temperature. and the problem is asking about what is the new pressure. Okay, for a gas at 1 liter and 1 atmosphere, we have here the initial pressure. It is 1 atmosphere. So the equation that we can use, guys, is like PV over temperature is equal to constant, and from here we can do P1 V1 over T1 is equal to P2 V2 over T2. This is the equation that we need to use. So I have initial pressure, which is 1 atmosphere. I have initial volume, which is 1 liter. I have initial temperature, which is 300 Kelvin. That's equal to final volume, which is 0.5 liter. Final temperature, it is 600 Kelvin. And final pressure, we don't know. So now we can solve for P2 is equal to 600 Kelvin times 1 atmosphere times 1 liter, and then divided by 300 Kelvin. Okay, multiplied by 0.5 liter. I think that's right. So 1 atmosphere times 1 liter times 600 divided by 300 Kelvin times 0.5 liter. And that's going to give me the new pressure. So the new pressure, guys, is equal to, so let's do this multiplication. I have 600 times 1 times 1, and that's equal to 600 again, and divided by 300, that's equal to, and then multiply by 2, and that's equal to. So we have four atmosphere. Okay, this is the new pressure, okay, which is D. So D is the right answer here. Okay, this is for problem 14. And for problem 15, let's see what do we have. So for problem 15, we have 2 mole of gas to occupy 44.8 liter at standard temperature and pressure. What's the volume for 1 mole? Okay, it is a relation between volume and number of moles. So we have V1 in 1 is equal to V2 over in 2, standard temperature and pressure. So that's going to give me the new volume, which is V2, is equal to N2 over N1 times V1. So that's going to give me N2, which is 1 mole, divided by the original number of moles, which is 2 mole, multiplied by V2, which is the original volume. So we have 44.8 liters, and when divide this by 2, that's going to give me 22.4 liters. Okay, so 22.4 liters, and that's the right answer. Okay, for number 16 now. So for number 16, for a gas at 10 liter pressure 2 atmosphere and temperature 300, what's the number of moles? Again, guys, the ideal gas equation. So from the ideal gas equation, you will see that PV is equal to nRT, and when you solve for number of moles, you will have pressure times volume divided by gas constant times temperature. Okay, so now number of moles is equal to the pressure is 2 atmosphere and the volume is 10 liters and the temperature is 300 Kelvin and the gas constant, and again I will give the gas constant from here. So let's do that. So the gas constant is 0.0, it is 0.0821. 0.0821, so this is the gas constant. Okay, so we can do here 0.8 and 0.08, so I have 0.0821. So now we can solve for the number of moles. So we have 2 times 10, that's going to give me 20, divided by 300, that's going to give me this number, and then I will divide by 0.0821, so that's going to give me 0.8. This is the number of moles, 0.81. Look at, so 0.81, so B is the right answer. Okay, so that is great. And if I come to number 17, so for number 17, what is the density of oxygen at 1 atmosphere and 273 Kelvin? So I remember, so we have temperature, we have pressure, okay, and we have the equation of ideal gas. So we have PV is equal to nRT. Okay, so we have pressure times volume is equal to number of moles, and the number of moles actually is the mass of the material divided by the molecular weight of the material. Okay, and then times temperature. Now what I'm going to do, I'm going to do pressure times the molecular weight of the material divided by temperature. That's equal to the mass of the material divided by the molecular weight. Divided by the volume. Mass divided by the volume. So that's going to give me the density. So now you will see that the density is equal to pressure times molecular weight divided by temperature. So we know the molecular weight for oxygen. So maybe we can have this standard from here. So the molecular weight of the oxygen is 32. So now I will have density is equal to pressure, which is 1 atmosphere, times molecular weight, which is 32 for the oxygen molecule, and then divided by temperature, which is 273 Kelvin. And you can see that rho, the density, is equal to the calculator. So we have 32 times 1 and then divided by 273, so that gives me 0.11. Okay, let's see if I made gram per liter. Oh, gram per liter. Oh, let's check the units. It is a very good idea always to check the units. So what I have here from my work, so from my work I have 0.11 atmosphere, and the molecular weight actually is a gram per mole and Kelvin. These are the units that we have. Okay, so let's double check. Yes, we need to do some conversion. We need to do some conversion here. Did I miss something here? So I will start reviewing from the beginning. So I have PV is equal to nRT, and that's equal to a number of moles is the mass of the material divided by M, which is the molecular weight, and then times R, the gas constant, and then times temperature. Oh, I see my mistake, guys. I just forgot to include R, which is the gas constant. It happens. So I need to have R here, okay, and I need to have R here, and I need to have R here, and also I need to divide by 273 Kelvin times the gas constant. Okay, so maybe having this typo will require us to go through the problem again to have right calculations. Okay, so maybe I need now to ignore this part and ignore this part. Okay, this is a volume, this is the mass. Mass over volume is equal to rho, which is density. So maybe I need to redo this again. So I have PV is equal to nRT. I know that the number of moles is equal to mass over molecular mass multiplied by R, which is the gas constant, and then multiplied by temperature. So we solve for density, so that means we have P, which is pressure, times M, the molecular weight, divided by gas constant times temperature is equal to the mass of the gas divided by volume. So that's equal to density. So now we have right equation. So now density is equal to pressure times molecular weight divided by R, which is the gas constant, and then multiplied by pressure. Temperature. So now I will maybe come here. So rho is equal to pressure. So the pressure is equal to 1 atmosphere times molecular weight, which is 32 gram per mole, and then divide the whole thing by R, and R is equal to 0.0, I believe 8, let's see that number here, 8 to 1, and then times temperature, which is 273 Kelvin. Okay. I think we need to double check. We need to double check the units of the gas constant again. So maybe I need to go. Yes, this is not the gas constant. Just double check the units of the gas constant. So the gas constant, units. Okay. So let's see here. we can get the units on the from the ideal gas equation. So this is one idea, and maybe here, so liter atmosphere per mole Kelvin. I think this is what we need, guys. Liter atmosphere per mole Kelvin. So I'm going to come back here. So the unit for the gas constant is liter atmosphere per mole Kelvin. So for the gas constant, which is 0.0821. Okay. Now, from this equation, you can see that the atmosphere will be cancelled with atmosphere. 1 over mole would be cancelled with 1 over mole, and Kelvin right here will be cancelled with Kelvin, and I will end up with this unit, which is gram per liter. And I think this is what the problem is looking for, gram per liter. Okay, let's do now the calculations using the calculator. So I have now 32, the molecular weight for the oxygen, divided by 0.0821. That's equal to, and then I will divide that by 273, so 273, so that's equal to, I have 1.427, which is 1.3, so B is the right answer. Okay, so we have rho is equal to 1.43 gram per liter. Okay, so 1.43 gram per liter. Okay, so this is for problem number 17. Okay, so my mistake early that I didn't include R, which is the gas constant, so that was like that was a typo, prevented us from having the right answer. But now we included R, the gas constant, so you can see now we have the right answer. Okay, I will now move to problem 18 and see how can we do this problem. So 18, in a mixture of gases with 2 mole of nitrogen and 1 mole of oxygen at the total pressure of 900 torr, what is the partial pressure for oxygen? So we have two moles of nitrogen, and I have 1 mole of oxygen. Okay, so that means, guys, for the oxygen, the partial pressure for oxygen actually is equal to 900 torr, and the torr here is a unit to measure pressure, divided by 3. So 900 divided by 3. So that's going to give me 300 torr as pressure, as a partial pressure for oxygen. So if you have two gases with two different pressures, those pressures are going to be added together. Okay, and you can see now the pressure from nitrogen is 600 torr and the pressure from oxygen is 300 torr. If we have them in one container, you need to add those two pressures together, so that's going to give you 300 torr. Okay, so for 19, if carbon oxide is at 0.5 atmosphere and helium is at 0.75 atmosphere, so what's the total pressure? I answered this question, guys. So you need to add the pressure from carbon oxide plus pressure from helium. So now you have 0.5 plus 0.75 atmosphere. So that's going to give you, so let's see here. So we have so 0.7 and 0.3, that's going to give me 1, so 1.25 atmosphere. So this is the total pressure. Okay, so just add them together. You need to add the pressure from carbon oxide and the pressure from helium. So that's going to give you the total pressure for the whole system. I'm done now with the practice problems from chapter 13. Going to go now to the practice questions, conceptual questions from chapter 14. Okay, so thank you very much.